file. So, for the benefit of the recording, um, this is Derek Ward-Thompson speaking, and I'm going to be talking about magnetic fields and star formation. This is a variation on a talk I gave at Astrofest, I believe last year in 2024. Um, but it's slightly enhanced because the talk at Astrofest, I only had a half an hour, I think, and so there's a little bit more detail in this. Um, and whenever I talk to astronomical societies, I always find that they want to hear the very latest. Well, I promise you, you will, because at one point I will actually be showing you things that I was working on this afternoon. So that's hopefully pretty much up to the minute. Right, so that's the now. Share screen. As I say, I'm more familiar with um, Teams
It's
normally than
down the bottom of the screen. There
it's
should
the
be a
green
green
one.
one.
Yeah, I
Yep.
got it. It's the green button. Here we go, and hopefully you are now seeing what I'm seeing, and I can click on slideshow and from beginning. Please tell me you can see my first slide.
Yes, we certainly can.
That's fab. Excuse me, just bear with me 1 second. Because hopefully you will also be able to see my cursor. Is that true? Can you
Yes,
see my?
yes, we can.
That's great. So I can point at things and know that you're seeing what I'm pointing at. So, I must say, actually, before I start, it's a great honour to talk to this particular group of people. Um, I was a member of the BAA myself in the 1970s um, as a young member, and I do think the BAA is a fantastic organisation. So it is a real honour to be talking to you tonight. So star formation, magnetic fields. How does it all fit together? It was a lovely introduction, by the way, because you're absolutely right. That's always been the classic question at every star formation conference I've ever been to is, but what about the magnetic fields? And that's exactly what we're going to talk about tonight. So I called this the star formation conundrum, and because for me and for many of my colleagues, this is probably the most important question in our area. The star formation rate in our galaxy is only 1/10 of what it should be. Now, what do I mean by that? By what it should be is if everything were in free fall gravitational collapse, we should be seeing 10 times the amount of star formation that we are in our galaxy. Um, just to clarify, free fall collapse, I guess you all know what free fall is. Free fall is when you step out of the aeroplane and a few seconds later remember that you've forgotten your parachute. Gravity wins. And so if you have a cloud of gas and dust and what have you in the interstellar medium, um, if it was all just collapsing as gravity predicts, that's what we call the free fall situation, and we would have roughly 10 times the amount of star formation we see in our galaxy. I'm going to restrict myself to our galaxy because I find that one galaxy at a time is enough to think about. And yeah, okay, call me parochial. I accept that. But it has quite far-reaching implications. What we measure across our galaxy on average is about a star formation rate of about one solar mass per year. So somewhere in the galaxy, every year, one solar mass type star forms. That's, a sort of rough order of magnitude. But if you do the calculations, it should be 10. Should I have 10 solar mass stars or one star 10 times the mass of the sun, or some permutation in between? So something's holding it up. My hypothesis that I hope to lay out tonight is that what's holding it up is the magnetic field. And I'm going to do this not from theory at all, but entirely from the observations. And I should acknowledge my colleagues, the collaboration that I lead is called BISTRO, which is a very contrived acronym, as you can see, B-Fields in Star-Forming Region Observations. We have about 150 members, and we've had several hundred hours of telescope time, which is quite respectable. Rule of thumb: about an hour of telescope time on, I said that the JCMT, the James Clerk Maxwell Telescope, is worth about $1,000. They claim. So two-thirds of $1 million is not too shabby. The problem that comes with that, of course, is you've got to justify what you've done with it. So I hope by the end of the evening you'll think we've spent our time well. We're at the moment at about 45 papers. We're pushing 50. We're well over 1,000 citations. So, but we still haven't finished using up all the telescope time. I should say the James Clerk Maxwell Telescope is a microwave radio telescope in Hawaii that was built nearly 40 years ago now. I believe it was about 1987. I was actually bizarrely one of the first regular observers to go out there and use the telescope in the autumn of 1987. Um, Excuse me while I have a drink of water. Um, and for nearly 40 years, it's been churning out some fantastic results. And the way it stayed relevant and contemporary is by new um, new instrumentation. Every few years, new cameras, new instruments, new radio receivers delivered to the telescope, and it is still the largest telescope in the world at 15 meters, or for those of you like me who work in old money, about 50 feet, that works specifically at wavelengths below 1 millimeter. Its workhorse wavelength is about zero point 0.8 of a millimeter. So you can either think of that as extremely high frequency or very short wavelength radio, microwave, as I say. And one final bit of technicals just to tell you about before we start. We measure the magnetic field using the polarization of the incoming radio waves. Polarization is it can be explained as follows. The electromagnetic radiation, which is what light, microwaves, radio, infrared, all are part of, is what we call a transverse wave. So if the electromagnetic wave was coming towards you out of your screen, it would be oscillating like so, or maybe like so. Polarization is a measurement of what fraction of the incoming radiation is going like so, and what fraction is going like so, or like this, or like that. And the polarization direction that I'll be referring to throughout the talk defines which direction your light wave oscillates in the most. So it might be at 45 degrees, it might be due up and down, or whatever. And the reason that's interesting is because the region where the radiation is emitted, the magnetic field in that region specifically, tells you, um, determines in many situations the polarization. So if you can measure the polarization, you can infer the magnetic field where you're looking at, in the region you're looking at. And that's what we do. So I'm going to split my talk in two halves, not quite equal halves, but in the first part, I'm going to talk about passive star formation, and in the second part, I'm going to talk about triggered star formation, and I'll define those terms as we go along. So, a few years ago now, this paper appeared that basically defined the different modes of passive star formation. Passive star formation is where star formation happens because of gravity, just in the particular region where it is. Triggered star formation happens because of what happens in the neighborhood. And something happens in the neighborhood, like I'll show you later, a supernova that triggers or sets off more star formation. So, passive star formation has three modes. This is called the isolated mode, the slow mode, and the fast mode. The isolated mode, you've got just a bit of the interstellar medium, dust cloud, and cloud of dust and gas, and by just random motion, somewhere you'll get bits that are more dense than other bits, and occasionally you'll get some parts that are sufficiently dense that gravity will cause them to collapse to form a star. This stage in the middle we call a core or a dense core, and that's where we think stars form. In the slow mode, you get what's called a formation of an elongated structure, where it's actually easier for matter to fall in two dimensions rather than three, and this filamentary-like structure occurs first, but then along that, just by random motions, you get denser bits and less dense bits. So in this model, the cores form along the filamentary chain, and eventually some of the cores become dense enough to form stars. That's sometimes known as the filamentary mode of star formation. And then you get the so-called fast mode, which is where two filaments interact and caught at their junction, they form what we call a hub. Material then flows along all the filaments and still onto the hub. Dense cores naturally form and stars form in that. And that's sometimes known as the hub filament model. You'll notice none of this includes the magnetic field. And no one up to now has really tried to put the magnetic field into this scenario or any star formation scenario with any um, comprehensive basis or any uh, scientific observations to back them up. And that's what we're trying to do. So, I should one last comment. I will in the next few slides work along each row in turn. So I'll go along the top row, then the middle row, then the bottom row, and at each stage, I'll try to present you with an example from our observations where we've measured the magnetic field and try and insert magnetic field into this picture, which has not been done before. So here's the first one. On the left-hand side, we're in the top left picture, and the right-hand side, we're in the top middle picture. So what are we looking at here? We're looking at, in the white lines, which I shall refer to as vectors, the magnetic field direction just in the cloud. These come from near-infrared observations, and you can see it's fairly chaotic. The blue vectors in the center, here's a dense core. The blue vectors are taken from our observations in the microwave, which penetrate the dense cores. And what you see is that in the surrounding region, the field is all over the shop. In the dense core, the field is considerably better aligned. It's starting to sort of settle down in a particular direction. So, interestingly, we refer to this model. What we think is happening between the sort of low density phase of the cloud and the higher density phase of the core is in the clouds, you've got a lot of turbulent motions. And as the core tries to collapse, it becomes more dense. And actually, that prohibits turbulent motions. And so in the center of the core, you don't get nearly as much turbulence. And that's what we call turbulent dissipation. The turbulence dissipates out of the central core, and then the central core can go on to form a star. Our interpretation of this is that out here, the white vectors show us the magnetic field is preventing collapse or impeding collapse. But once you've got collapse happening and the field is aligned, then the collapse can carry on because the field has essentially carried away the turbulence. So I would say in this case, the magnetic field has acted to slow down the formation of this core. So in this case, we would say definitely slower than free fall. Here's a case just where you see the middle Okay, so now this one um, is again a dense core that's already formed, and these purple lines are a model of what a magnetic field might look like. And typically, where the core forms, the field lines get pinched in. You see this. Um, this is what we call the hourglass field. Um, that's very much an Americanism. Hopefully, you all, like myself, think of it as an egg timer. I recently was teaching this to a group of third year undergraduate students, and I said, hands up if you know what an egg timer is. Blank faces. Hands up if you've ever seen or used an egg timer. Blank faces. And I said, well, I can remember as a child my grandmother using an egg timer to time how long to boil an egg. And they looked at me like I was 1,000 years old. And I did feel old at that particular point in time, I must say. Anyway, that's by the by. What we've got here then is a comparison between the observations and the model. Remember, the model is the egg timer, the purple lines. The observations are the blue lines. The red is if we did have a perfect egg timer, where should the vectors be pointing? And I'd say the vast majority of them are the blue and the red are close to or absolutely parallel to one another. And so I would argue that this is a quite a good model of star formation, and people have done serious calculations on this. The model has the wonderful name of ambipolar diffusion. Please don't ask me to defend why it's called that, because I think it's a silly name as well. But you can make calculations and you can find out that it is slower than free fall, and in some cases as much as the 10 times slower that we need in order to explain the star formation rate across the galaxy that we see. So I'd say that so far now that's 2-0 to the magnetic field. Then we go on to something slightly more complicated, and this is the right-hand picture now of the top row. And this is a region where we formed a dense core, and we've actually formed the first star in the middle of the dense core. It's about here. And one thing we know about young stars that have just formed is that they are exceedingly energetic, and they have what we call outflows, not dissimilar to the solar wind, but much, much more energetic, and predominantly coming from the poles of the very young star. So that's what we see here. The sort of light blue contours mark this outflow going towards us. There's another one behind that's going away from us, but we can't see it because it's pointed into the cloud. But anyway, once again, the black lines mark the magnetic field, and over here you've got an interesting, well-ordered magnetic field. In this bit, you've got a different ordering, but nevertheless well-ordered magnetic field. Where the star is formed and blown out this what we call outflow is completely messed with the magnetic field. You see these lines running along the edge of the outflow. So I think what we can say in this case is the magnetic field might have played a role, but It's not playing a significant role anymore, and we're just looking at a state that's too late. So let's walk our way along the middle row, the filamentary model or slow mode. The basic idea of this is that material follows these blue lines and falls down onto a filament, which is the gray area. Once the filament's formed, it itself starts to collapse under its own self-gravity, and that's the black arrows. But in addition, once you form a lump at one place, other material either side of it in the filament then falls towards this dense bit, and that's how you form. So I would say this is this situation where you haven't formed dense cores yet, but stuff's on its way. Now, here's some real data. This is actually from the American Spire spacecraft, but nevertheless, you can see in the yellow this bright filament. Um, the green are the measurements of the magnetic field. And lo and behold, the observations are agreeing with the theory. And what we think is happening in this case is the magnetic field is funneling material down onto the filament. So it's quite tricky in a case like this to say the magnetic field is slowing things down. It might actually be making things faster because it's funneling material onto the filament. So I would say in this case, probably the jury's out. Here's another one, but we're now well, in this right-hand picture, you can see examples of the right-hand cartoon and also the middle cartoon. The blue, sorry, is supposed to be the filaments. The black lines is the large-scale field. So you can see a lot of filaments where there are no cores, which is this one. But I would zoom in on this particular filament where it has formed a core. This is that core. This is a zoom in of that. Again, the black lines give you the large scale field. Notice how inside the core, these are our measurements, the field still does what the large scale field does, which is stay roughly perpendicular to the filament. So it looks like this is another case that follows the model. Again, whether that's helped or hindered, difficult to say. I would say it has hindered things slightly because it's taken that bit longer to form a core in the filament simply because everything's having to cross magnetic field lines to move along the filament. So I'd argue that this one's not so clear cut, but nevertheless, it's probably slower than free fall collapse. Another one that's in the same situation, but this is much, much more complicated because we've got a filament, rather three filaments, forming a triangle. Now, the yellow lines here, the yellow vectors, they're the large scale magnetic field. The red vectors are our measurements of the small scale local magnetic field. And the blue lines are meant to indicate the direction of the filament. So if the simple filamentary model were correct, then the 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 magnetic field, the red ones, should be perpendicular to the blue ones, and in most cases they're not. Although right here, filament C, core number 4, it is actually quite close to perpendicular. Furthermore, the local magnetic field is pretty much parallel to the large scale field. Nothing's had time to mess about with it. So we think this is essentially a pristine core um, that's just following the initial conditions that were set up, what the cloud looked like originally. And so we think this is a case where we're moving from what we call the magnetically dominated regime, where the red vector parallels the yellow ones, before we move to what we call matter dominated, which is where the matter messes with the magnetic field. Um, and this cartoon here is just intended to show that. And once again, this is our what we call ambipolar diffusion model, which is definitely slower. Finally, the right-hand side of the middle row, I'm going to Orion to look for an example of this, which is where you've got cores and stars in the filament. The left-hand picture is our data of what's known as the integral filament in Orion. We think what's happened here, you'll notice the magnetic field here is sort of horseshoe shaped, and here is upside down horseshoe shaped. So two cores have formed, but something interesting's happened. This cartoon is meant to show what we think's going on. You've got the field that starts out perpendicular to the filament. You form two dense cores relatively close together, and they fall towards each other under their mutual attraction due to gravity. Because they all contain some fraction of charged matter interacts with magnetic fields, so as they move, they pull the magnetic fields with them. And that explains the double horseshoe. But pulling the magnetic fields takes energy, and that slows them down. And this situation, I always say, reminds me of a bed spring. You can sit on the top of a mattress with a spring like this underneath it, and it helps to hold you up. So, what we think is happening here is what we call the bed spring effect, which is actually genuinely slowing the collapse. Without this effect, these two would have collided long ago and generated a huge number of stars. So we think in this case, the magnetic field is definitely helping to slow things down. Final one in the middle row, where we're also at this stage, but a slightly lower mass case because we're in Taurus now. We got here's a filament. Here's the magnetic field, the large-scale magnetic field in yellow and also in light blue, just from two different ways of measuring it. Generally going perpendicular to the field, to the filament. Zoom in, And the red vectors now are the field, and frankly, they're all over the shop because star formation has already started in here. Um, so, well, actually, this one has no star formation. This one has formed a star, and the blue and red is its outflow that we were talking about earlier. So the field hasn't moved much from that. This one also has an outflow. There's the blue and the red that's rotated to be almost 90 degrees. So um, the first thing I'd say about this is nobody understands this fully. We're all struggling with this one. We're arguing about it at the moment. Um, but at the same token, I think we have to say the same about this square as we did about the top right-hand square, that we're now looking at things too late. The interesting stuff's all happened. Whether the magnetic field was going to be disrupted or not has all been decided upon and happened. And so we can't actually say what role the magnetic fields played in this case. So let's move to the bottom row, the so-called fast mode, where filaments rotate and join each other and so on. And you've got this messy region. This is quite much further away. Orion, that we were talking about earlier, excuse me, is at about 1500 light years. Taurus, that we were talking about earlier than that, is about 400. This one, excuse me, is more like 3000 light years. So we're much further away, much higher density, but nevertheless, this is what this hub filament predicts. But I hope you can see the vectors on here, all in white, the magnetic field. Basically, it's all over the place. Can I say whether the magnetic field is slowing the process down? No. Can I say whether it's speeding it up? No. All sorts is happening. Going to take quite a bit more work to try to understand what's going on in this one, which we think is basically the bottom left-hand plot. Here's another one that's frankly a mess, very slightly further away than the last one. So, hub filament, okay, you've got two filaments in here. Magnetic field's going perpendicular to the filament. In here, it's more or less aligned with the filament. In here, it's more or less at 45 degrees. How the heck are we supposed to explain that? So this one definitely, the jury is out. And then finally this one, which is more like the right-hand side, because we've got a star cluster has formed in the middle of here. The magnetic field seems to have superseded the filaments. The filaments are the various coloured lines. You see how the magnetic field looks like it's just spiraling in and just ignoring the matter altogether. Now that's open to interpretation, but you could make a a plausible interpretation of that and say, well, actually, the magnetic field is funneling matter into the center. It could be actually speeding the collapse, not slowing it down. So this one doesn't help our cause. So let's move on to triggered star formation, as we call it, the opposite of passive. Um, there are various agents or phenomena that can act to trigger star formation, to start it off externally, and I'll go through a few of them. First of all, O-type stars. So, O-type stars, as you know, are the most massive. Um, they are the shortest lived of any of the types of stars. Therefore, if you see an O star, you know it's young. This left-hand picture is a picture. Well, you might be familiar with the underlying picture. It's the Hubble picture of the so-called pillars of creation. And we put on it, with our white vectors, the magnetic field direction. And I want to draw your attention to the middle pillar. Look at this. Magnetic field's running exactly along the pillar. There you see it. I'll zoom in. This is some shorter wavelength observations. This is the near infrared, so it can detect the magnetic field outside of the pillar and see that it's much more random, much less well aligned. What we think is happening here, so going to this right-hand picture, if you look at this, somewhere up here, there is a small cluster of O-type stars, very young, very boisterous, very energetic, um, very, uh, very strong stellar winds, just generally uh, the local bullies, shall we say. And we think what's happened is this is a sort of cartoon. As the bullies push their um, influence, we cause what's called a shock. Those of you who, like me, can remember Concorde will know what a shock wave is. It's what we used to call the sonic boom. That's one of the manifestations. It's something like that's happening here. So from those nearby O stars, you've got what we call a shock front or a sonic boom, and it's approaching um, this area. And our hypothesis is that at the tip of each column, you've actually got quite a smart cookie. But it's not just that, it's actually quite dense. And so when the shock front hits this, it's more or less stopped in its tracks, but it carries on either side. So if you've ever been to the beach and seen a rock, large rock stuck in the sand, and um, you, you know that the wind has been blowing from a particular direction. You can see the wind shadow behind the rock. You see the wind-blown sand either side, and then behind it you've got a shadow. And that's exactly what's happening here. You've got a wind shadow. The rock stops the approach, and either side it carries on. And that's how the pillars are formed. That's that's how you do this. And then this situation develops into this one where you've got a pillar and the shock front is trying to eat away at the pillar. But as Kate Pattle showed, she was one of my PhD students. Actually, what is supporting the pillar in this case is the magnetic field. by calculating the mass present, the magnetic field strength, and so on. She was able to say that, and that went into her thesis. Um, and supported it to the extent that we can't say definitively, but it looks very, very promising that actually these pillars are actually 10% longer lived than they would have been if they hadn't had the magnetic support. So that's interesting. This is a case where the magnetic field is definitely slowing things down, doing what we want it to do. Um, Supernova remnants. That's another goodie for triggering because, as you all know, a supernova is a very massive star that goes kablooey and throws out all sorts of nasties into the interstellar medium. Um, in addition to that, it also generates one of these shock waves, our so-called sonic boom. Incidentally, I used to live in South Wales, to the west of Cardiff. I taught at Cardiff University until about 10 or 12 years ago, and we lived there for about 15 years. And during our time there, um, Concorde was still flying, and sometimes you could actually hear the sonic boom as in the evening as Concorde was coming home, because as I'm sure you know, Concorde was only allowed to go supersonic over water, and it would come up the Bristol Channel because that was the closest bit of water to Heathrow on its route back from JFK. And sometimes, if he was late, I think the pilot kept it at more than Mach 1 for slightly longer than he should have done. I've heard the sonic boom on numerous occasions. I'll try and tell that story to students today. They haven't a clue what I'm talking about. Anyway, supernovae. We've got this. This is some of you may be familiar with it, the Rosette Nebula. We looked at a portion of that with the Herschel Space Telescope, and then we looked at a portion of that with the James Clerk Maxwell Telescope, and then we looked at a portion of that with the measuring the polarization. And we found an interesting structure, which we christened the diamond ring. You can see the ring and and there's the diamond. And interestingly, for part of that, we found that the magnetic field had actually aligned with the ring. So in the middle of here, a smaller supernova has gone off, or a more recent one than the one that caused the rosette. If you look here, the magnetic field is trying to follow the ring of the supernova remnant, and that is potentially helpful for us because rather than let the shock go flying through the interstellar medium, the magnetic field, if you do the calculations, is actually slowing the expansion of that shock. I can't tell you definitively it's doing so by a factor of 10, but nevertheless, it is helping. So I think in this case, we can say that it's causing slower star formation. Now, at the start, I said I'm going to take you to the very cutting edge of current contemporary research. This picture that I'm showing you here, this is what I was working on this afternoon. So the, this is really up to the minute. So please don't expect any definitive answers here. This is purely speculative as to where we've got. What we've got on the left-hand side here is a JWST image, which some of you might have seen. It was released as part of the first anniversary celebrations of JWST. Excuse me, I'm going to drink water. And it is of one of my favorite regions, Ophiuchus. Oh, by the way, just as an aside, here's a tip. If you are talking to a member of the public and you say, "Oh, I'm a keen amateur astronomer," and they say to you, "What star sign are you?" That's one of my least favorite questions, by the way. I always say, "Oh, I'm Ophiuchus." Because Ophiuchus is actually in the plane of the ecliptic. It is the 13th star sign, and it really annoys astrologers. So please, by all means, you use that one. Also happens to be one of my favourite star following regions. Anyway, what we've got going on here is a huge amount of chaos, and some of this has never been seen before or been interpreted. If I can try and talk you through the chaos that's going on, right in the middle of here, you've got a very, very young star. And then coming either side of that, this is one of those outflows that comes along the poles of the star in red. Um, and by the way, the NASA publicity people never care about which way's north and which way's east. This is just to try and orient you. They're just trying to make pretty pictures. But fascinatingly, we can do science from these pretty pictures. And as I say, so we've got an interesting little outflow here. If we look at the magnetic field, so we took that picture and we put our magnetic field on it, which is is the white contours. There's green contours, which I hope you can see, but they haven't reproduced terribly well. They're from the far infrared, 90 microns, so about a factor of 10 shorter wavelength than we are. But if you look at our magnetic field that we measure around here's the outflow. So you've got a field that's doing this, and it's sort of S-shaped. I looked at it and thought, maybe. Do you remember the one right near the beginning where I showed you the magnetic field running up the edges of the outflow? Because the outflow is coming pretty much towards us. Here, we're seeing it pretty much sideways on. I think we're seeing a spiral magnetic field. So not only is the magnetic field coming up the sides of the outflows, it's spiraling around the outflows as well, literally like a corkscrew. So in the paper that I'm writing at the moment, as I say, was working on this afternoon, we're going to say, look, this is what we think's going on. We've got a spiral corkscrew magnetic field running around the edge of this outflow. So in the middle of here, as you can see from the left-hand picture, we've got a this thing is actually a B-type star, and this area here is what's known as a photon-dominated region, which you may not have come across, but it's a slightly lower energy version of what astronomers call an H2 region. They have a lot of ionized gas. And so we're studying what's happening in here, which is what the green vectors from the far infrared are telling us about. Um, because this is absolute up to the minute, I can certainly not give you a definitive answer yet. We're still doing the calculations as to what's winning where. You see this thing here that we've called the arch. The magnetic field seems to be following it. Whether this means star formation is happening faster or slower, I can honestly say to you, I haven't a clue. But we're working on it. And just finally, first time I saw this picture, ignore all the lines on it, that came from JWST. That's what I saw. Some kind of giant space monster fighting a squid. Um, yeah, okay. Some of my friends think I'm a bit odd as well. Anyway, the last example I'm going to show you is the center of our galaxy, what's called the central molecular zone. So we're not zooming in as close as the black hole here. Uh, we're still a few hundred light years across here. But if you look towards the center of our galaxy, you see a whole raft of regions of star formation that looks as if it's wanting to make a figure of eight. So we measured our polarization and calculated our magnetic field direction along them. And we noted that there was much, much more spread in this left-hand half than the right-hand half. We also note that there's a lot more star formation going on in the left-hand half compared to the right-hand half as well. So, how do we interpret this? Well, are these things a real structure? That's the first thing we had to ask. And the way you do that is you look at the Doppler shift of the material. So this bit that's in red, that's this bit. And if you find something that's continuous in 2D space on the sky and continuous in 3D space, in velocity space, then you can believe that it's a real structure. This light blue one, well, that's this. It's a real structure, but offset in velocity from the Doppler shift from the red. And finally, we've got this bit, the blue. Again, this is another real structure, but it's offset in velocity from the red one. So our interpretation, but down here, the last bit of the figure of eight, we haven't enough data to be able to tell. So our interpretation of this, and we call this the bagel, is that it's some kind of structure that looks like this, and then this, and then this is the missing bit that we've filled in. And this could be an elliptical orbit that's just precessing, and that's quite possible, quite likely. But going back to um, why was this side less scattered than this side? This side, we think, has what we could measure has less star formation. Therefore, we think it represents the initial conditions. What was there? The primordial magnetic field. And the primordial magnetic field is running along the filament. Over here, we think the primordial field has been destroyed. Question is, has the field helped to organize the matter into, the star formation we see, or is it hindering collapse? And that one, the jury's still out. This is a very, very recent. This was published by my former PhD student within the last 3 months, and the community still hasn't reached a decision on this one. So, coming to my conclusions slide, can magnetic fields answer the question, the conundrum, as to why the star formation is only 1/10 as efficient as it ought to be? Let's just run through what we've said. In isolated mode, our first couple of regions we looked at was yes, it's definitely slowing things down. The third one we looked at, well, we were just looking too late. So my argument is overall that's a yes. The middle line, if you remember, of the passive mode cartoon, first one was too young, we couldn't say. The middle one, yeah, that it's probably doing the biz. Ditto the next one and the Orion. And by the time we got to the last one, it was too late. But again, I would say overall, that's a yes. And the bottom row, well, that was the one that we really couldn't tell. It's unclear. The hub filament, some places you see the hub, the field going perpendicular to filament, some places you're going parallel. In terms of triggered star formation, if you remember the pillars of creation, we said yes, they pass muster. The supernovae, maybe maybe having the magnetic field there is slowing the expansion of the shocks, and then but finally the Ophiuchus one I was telling you about that I was working on today, we still can't say. And the one at near the middle of the galaxy, that's really too complicated for us to say anything about it yet. So I would say my overall overarching argument is yes, the magnetic field is playing a role. It is slowing down star formation in some cases. Is it enough? In enough cases, I don't know. And I'll leave it at that. Thank you.
Right, Derek, thank you very much. I'm going to throw it open to questions. Does anyone have any questions?
I just wanted to say thanks for a wonderful presentation.
It's
Thank
most
you.
appreciated. Diane, do you want to just unmute yourself and shout it out, or you'll need... No, can't hear you. You've got no sound at all.
Oh, how's that? Is that better?
Much
Yes.
better.
Ah, thank you. Right, thank you, Derek. Good presentation. An observation
Yeah.
that about eight timers. It's also
Yeah.
most current generation of children don't know what an A4 hole punch is or what a ring binder is.
Or possibly an egg.
And my star sign is skeptic.
Oh, I love it. I love
Right.
it.
And the
I
question,
love it. Um,
you were talking about the magnetic fields. Do
yes.
you know if they're all polarized in the same direction, i.e. left or right hand polarized?
Yeah.
And are the fields flowing from north to south, or are some of them monopole?
Ah, no, we have not found a magnetic monopole. And the limitation of our method is we can tell the direction the field is, but we can't put an arrow on it. So we don't know whether it's going top to bottom or bottom to top. We're that's the limitation in terms of current technology.
So to quote Patrick, we just don't know. But thank you.
Oh,
A very good
the
presentation.
great
Thoroughly
Patrick
enjoyed it.
Moore.
Thank
Yeah.
you.
Actually, by the way, I'd be delighted if those of you who haven't got your cameras on would switch your cameras on, even if you don't want to ask a question. I just find it lovely to see the audience, if that's okay, please.
Okay, I'm going to take one question as it's a supplement to Diane's, and
Mhm.
then I've got two people with their hands up for questions. Um, can you tell anything about the orientation, or are you just seeing and strength, or are you just seeing a
Ah,
helicopter view looking straight down, and you have no feel for whether it's tilted in the line of
exactly. Yeah,
view?
no, that's a very good question. All we actually measure with the observations I showed you is the direction in the plane of the sky.
Okay.
We can't tell whether it's tilted towards us. If it's going top to bottom, we can't tell whether the top's tilted towards us or the bottom. There are other measurements that you can make, and the chief amongst those is what we call Zeeman measurements, the so-called Zeeman effect, where you can get an idea of the strength of the magnetic field along the line of sight. And we have made several attempts to put those together, and in some cases we've been successful. In many more cases, we haven't. And I deliberately didn't go there because it's a real minefield. Um, but the interesting thing is that if you measure, okay, so this is really, and some astronomers will argue with this, really what we would call a second order effect. If you measure the amount of what we call dispersion, so how much variation there is from all of the vectors being exactly parallel, then, and you couple that with your measurement of independent measurement of the turbulent velocity, you can get hold of the relative magnetic field strength, or at very least, the relative energy, potential energy held by the magnetic field compared to the potential energy held by the velocity field. And that's interesting because and that was what we were using in the case where I was saying, if you remember the triangular filaments, we were using that in the case where we were saying whether we were going from what I called magnetically dominated to matter dominated. It's not a direct measurement. It is a calculation based upon a direct measurement, which naturally, therefore, like all such calculations, has implicit assumptions. But it's actually, not too bad, I would say, and it's the best we can. It's the best we can do.
Okay, thank you. I'll take you in alphabetical order. Amy.
Thank you very much. Thanks, Professor, for the presentation. I was curious to know what exactly is the physical cause for the influence of magnetic fields on star formation. And once upon a time, it was believed that stars form because of the genes instability in fluids, the
Oh,
gravitational instability.
right. Yeah, no, good question. Jeans was a genius. Sir James Jeans, a brilliant man. He was writing down equations. He didn't have computers to help him. And so he had to make the assumption that the dense core he was looking at had a uniform density right across it. And then if you make that assumption, then you can actually write down relatively straightforward equations. I say that, but everything's straightforward after someone else has shown you how to do it. It takes a real genius to do it first time. And he could work out what you needed in terms of temperature, density, radius, etc., before you were ready to collapse. That's all well and good, and that gives you, actually, it gets you a long way. It's surprising how many cases that works. But uh, if you're looking at real world, real universe situations, you never find a large region of uniform density. The dense cores are always denser in the middle and coming out to less dense at the edges. And so we have to go beyond the gene's mass. And then the best way to look at things are what we now refer to as the virial mass. And basically, all the virial mass does and is a comparison of the relative potential energy in the magnetic field energy, the gravitational potential energy, and the velocity potential energy. Well, you remember a Brownian motion experiments at school. The velocity of the atoms tells you like the temperature, but sometimes the velocities are to do with the turbulence as well. So the virial takes you one stage beyond the genes. What we're trying to do is go even one stage beyond that and actually try and measure all of those numbers and then compare them.
Okay.
Thank you. Tony.
Thank you. Fabulous talk, Derek. Beautifully illustrated.
Hi, Tony. Thank you.
I want to go back to your egg timers.
I knew you'd all love that one because I do.
Well, I wanted to tell you a companion story. I
Go on.
was a volunteer one day a week down at the National Museum of Computing at Bletchley Park,
Oh
where
wow!
we
I was
rebuilding.
just there. I was just there last year. It's a fantastic
Yes,
place.
well, I'm working on the EDSAC rebuild, which of
Oh
course is
wow!
full of fermionic valves.
Oh, really
Anyway,
exciting.
yeah, some sixth form students were around the other week, and
Hmm.
they happened to have a relatively young teacher with them. And he came over, and I said, "Are you interested in EDSAC at all?" Oh, he said, "Yes, tell me about it." Now he was about mid-20s, and he told me he'd done a physics degree, and he was a teacher, so you can make your own conclusion about that. But there you go.
Mm.
I said, "This has got valves." And I held up a valve and he looked at me completely blankly, which is what I expected because nobody knows anything about valves if they're not older than about 50. So I said, "All right, it's actually like a transistor." And he looked at me blankly. He
Oh
hadn't
no!
he hadn't actually heard the word transistor.
Oh, you're
And
kidding me.
I thought at first he was putting in my leg. No, it can't be. And I said, well, what did you do in your degree? And he sort of waved his hands about and said, oh, I sort of learnt about waves. Um, and since
Did
transistors are
they
the
do any electronics?
since transistors are the building block of everything that runs the world today, I was horrified. And I did pity for those sixth form students, because when the apocalypse comes, they won't they won't have learned anything about how to rebuild the world.
Brilliant.
But
I
I did
probably
have
shouldn't ask this because it's a naughty question, but did he say which university he got his physics degree
no,
from?
I don't think I caught that from him. Anyway, I did have a slightly serious question to you.
Yeah, fire away.
Um, you you sort of blandly said these H fields, and you explained how they sort of come together and polarized, etc. But I always thought H fields were generated by these things. Are they everywhere in the universe? Did they come
Yes.
from the Big Bang or what?
And no, 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 no. If you remember your school physics, um, electric fields and magnetic fields are completely and utterly intertwined. You can't separate the one from the other. As soon as you get a moving charge, that generates a magnetic field. And um, because the entire universe is in motion and everything is in motion relative to everything else, nothing is nailed down, of course, then you will always get charged particles because some fraction of the interstellar medium, I think it's only about one part in a million, but that's enough of the medium between the stars, the interstellar medium, is charged. And so, whenever one of those charged particles moves, it creates a magnetic field. And
Right.
so, the magnetic field, yes, there was probably a primordial magnetic field created by the Big Bang, but it's continuously being recreated and re-strengthened by all of these moving particles. I'm sure every single one of you will remember a demonstration that your teacher did in your physics class when you were about 11 or 12, where they hung a wire down through the middle between the two poles of a magnet and passed a current through it, and the wire jumped
Yeah.
out of the way of the magnet. Now, that's the same effect, but in reverse, because what's happening there is you're generating an electric current down the wire, which in turn is generating an electric field around the wire, which in turn is interacting with the magnetic field of the magnet and forces the wire out of the way. And it's the same effect, just it's the magnet that's moving. It's the electric charge and the electric field that's moving that's creating a magnetic field.
That's very
Faraday's classic experiment. I don't know if you all know this story already, but apparently Faraday was showing this off to I can't remember which prime minister it was that came to visit him, but it doesn't matter. Um, and he showed this wire jumping in the magnetic field effect, which we all now refer to as the Faraday effect. And the prime minister said, yes, very very interesting, but what use is it? And Faraday said, I have no idea, but I'm sure you'll find a way of taxing it one day.
I love it.
And of course he was perfectly correct because as you all know, that's what drives the electric motor. So sorry, no inherent physics in that story. I just like the story. Any other questions, or is everybody really tired by now at this time on a Friday night? I must say, I'm really impressed by all of you and your stamina, as I say, at this time on a Friday night. But are there any final questions?
No, silence. We've been reduced to silence, which is usually a good sign. Derek, I would like to thank you very much for an interesting talk. Or I will say, if you are invited again, or if you know anyone who we would like to invite, we like a technical talk, and
Brilliant.
we like some detail and some meat in it. So that is very much appreciated. Thank you very much.
And if you email me, I'll put you in touch with various of my colleagues who give very good talks as well.
Excellent.
Fabulous.
Okay. Any other questions? Last chance. So I'm going to stop the recording and close us down. Good night. Have a good weekend. See you at the next session.
Thank you all for your company. I've thoroughly enjoyed talking with you. Thoroughly enjoyed it. Thank you all.